Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 22 of this course on machine learning for earth system science. So, today we are going to talk about hierarchical Bayesian models for spatio-temporal processes. We are still in module 3 where we are discussing machine learning for discovering new insights in the earth sciences. So, the concepts which we are going to cover today are as follows: hierarchical Bayesian models for sparse observations of latent processes. Secondly, the Markov random fields for priors on latent spatio-temporal variables, and third, estimation of latent process variables using the iterative approach. So, first of all, we may need to estimate the property or a variable that is not directly measurable. So, we have seen some examples of this in earlier lectures also. For example, in the previous lecture we talked about the heat wave, the binary variable. So, that is not directly measurable. There can also be other, so that is of course a conceptual variable that is like that does not exist, but there can be actual variables which exist, but they cannot be measured directly. That is, or even if they are, or like they can be, we can measure some noisy versions of them, but not but like the noise components might be quite significant. So, we may have some sparse observations of some related variable, that is, instead of measuring that variable directly, we can focus on some related variable for which we may have some sparse observations. Some sparse observation may be either sparse in either space or in time. But if it is in space, then we call it in situ observations, where like something like we have, suppose we are measuring global temperature, then we can have temperatures only at certain specific locations which may be distributed all over the world, but they are only specific locations. So, from that we have to somehow, from those sparse or in situ observations, they we have to get the global picture somehow. The general approach is that express the observable variables using some kind of stochastic models, and the properties of the latent variables are also modeled using stochastic models. Now, the inference is done using some kind of MCMC or Gibbs sampling to optimize or estimate the latent values. So, remember we had talked about in one of the lectures in module 1, we had talked about the observation model, data model, the parameter model and so on. So, this is related to that same matter. So, let us consider a couple of use cases of this. So, for the first paper which we will discuss today, this is a Bayesian hierarchical model for climate change detection and attribution. So, regression based detection and attribution methods continue to take a central role in the study of climate change and its causes. Here we propose a novel Bayesian hierarchical solution to this problem, which allows us to address several open methodological questions. Specifically, we take into account the uncertainties in the true temperature change due to imperfect measurements, the uncertainty in the true climate signal under different forcing scenarios due to the availability of only a small number of climate model simulations, and the uncertainty associated with estimating the climate variability covariance matrix, including the truncation of the number of EOFs in this covariance matrix. So, this covariance matrix which they are talking about, this is related to the variability. So, like when we are considering the that is we are considering the various or any particular variables related to the climate, we have only some observations, and in the other locations or time points we have to estimate it using by using the covariance structure or by knowing the covariance relations with the other locations and times where the observations are present. However, these covariance structures are often not well known or cannot be well represented. They may be known very approximately. So we apply Bayesian model averaging to assign optimal probabilistic weights to different possible truncations and incorporate all uncertainties into the inference of regression coefficients. We provide an efficient implementation of our method in a software package. So basically the idea is as follows: corresponding to the vector y of true temperature changes. So let us say that in different places or different locations in the world, the temperature change that is expected to take place in a given period of time, that is those values are taken in a vector called y, and then we have vectors x1, x2 up to xm representing the temperature change that would have happened under the m different forcing scenarios. So like we have let us say m for like we do not know which what exactly will happen in future, but let us say we have m simulations of that, and then in each of the cases we have some in each of the scenarios also we may have several observations, because not all these observations all these simulations, they have some uncertainty associated with it. Even in one particular scenario, let us say x1, we need to have several simulations or several runs of simulations, and that is what that in some sense captures the uncertainty of the simulations or the spread of the simulations, because even in a particular scenario we are never able to say for certainty what kind of change will take place. So that is why we need an ensemble of values from one scenario, and then on top of that we need an ensemble of scenarios. So let us say that we have m scenarios, and from each scenario we have several observations. Also denote by C and n cross n covariance matrix characterizing the internal climate variability without any forcing. So this C is the covariance which we have already talked about. Now so there is this kind of a so first of all, let us say that the true temperature change y, it is a it follows a Gaussian distribution whose whose mean is can be expressed as a linear combination of the different scenarios. So we can say that each scenario has certain probability. So we do not know those probabilities, but if we knew them, then the we could say that the actual change that will happen is some kind of the probability weighted linear combination of these individual scenarios, and then of course the covariance is there. Now if you consider so I already said that there are so many different observations. So so many different runs of a simulation. So in any particular run of a simulation, let's say that yi is the true value. So y is the true value and yi is what is observed, and so it we can say it follows this kind of a Gaussian distribution. So this is you can say this is the yi is the measurement of y, that the true variability at all locations across the world. So for that we use another Gaussian distribution, and then even for the x's, so I already said that there are there are m scenarios, and in each scenario there are certain number of runs or the simulation runs. So let us say those runs are denoted by this variable L. So in the lth run, the xi is let us say I is a particular location, then the temperature change at any given location I in the lth run, given all the given the temperatures at all the temperature changes at all other locations, that again follows a Gaussian distribution for which we need this C as the spatial covariance structure, because the covariance what it takes into account is the spatial relationships. So I and j are two locations, so this C in a sense incorporates the variance between the covariance in between them. So we have y which is a collection of these of the actual y variables like this, and we have x, that is the different runs from the simulation runs from the different like according to the different scenarios. So like we have L1 number of x's from the simulation 1, we have L2 number of x's from the scenario 2, and we have Lm number of x's from the scenario m, and so on. Okay. So so basically we have so both x and y are random variables in a sense. So we write their joint distribution in terms of the different model parameters. So we factorize that joint distributions as follows. So first of all, we want to have like a distribution x. So this is for the model runs. So here we this joint distribution can be factorized in like in a particular way, again over all the simulation all the scenarios and each run of the scenario. So like assuming all the simulation runs to be independent, we can like just express each of the individual simulations as products of each other, and then again within that we can do the simulation like we can express it in this way. And similarly for y we can express so like we already know the relation between y and x. So this is the relation, so it can be expressed in another way also. So now the thing is, we have so many other variables like these c and so on, which like that is what we are finally interested in is the joint distribution of y and x. So so the c and all these things, that is c itself, we can write it in using these as a b, k, b prime, etc., where b, k, sigma, these are all model parameters. So these all those model parameters are like they are compressed within this theta r, and r is like, so like this for c we can consider, so c is the covariance matrix, but we can like it's a it will have a certain rank, but we can go for a low rank approximation of r. So in like whenever we are considering any particular model, we will consider only a certain number of so only a certain number of principal components. So that number, let that number be r. So so that the full covariance, instead of having the full covariance matrix, which might be difficult to measure, we can go for a like a truncated or as they say a low rank version of the covariance matrix. So these are the like the truncated model parameters. And so so what also these betas, these are another set of model parameters. So what we need to do is we need to estimate these through the process of Gibbs sampling. So like we again will not go into the details of the Gibbs sampling here. What we will instead do is that we will go for the this Bayesian like inference. So like once that once we do the Bayesian inference, then we have the results, and here like these green and the red curves, these indicates the yeah the like if you see the posterior distributions beta 1, the anthropogenic forcings in red, and beta 2 the natural forcings in green for each UF translation. So like this is the different scenarios. So like in one scenario where we do not have any human induced impacts, so like here is what the that is the posterior distribution in that case looks like, and in this I mean the posterior distribution on y, and in this case we are talking about the other scenario where we have the posterior distribution from the red, that is the when we are considering the anthropogenic changes. So as you can see that there is a clear difference between the temperature in the absence of according to natural forcings, which is this green curve, and in the presence of anthropogenic or human induced forcings, this is the curve, and so on. So next we come to another similar case study where we use Markov random fields for modeling of for mapping of geofluid distributions from seismic velocity structures. So this like in this domain of seismology, so here like in this paper we applied Markov random field model, which is a Bayesian probabilistic method to the spatial inversion of porosity and pore shape in rocks from an observed seismic structure. Gaussian Markov chains were used to incorporate the spatial continuity of the porosity and aspect ratio of the pore shape. Synthetic inversion tests were able to show the effectiveness and validity of the proposed model by appropriately reducing the statistical noise from the observations. The proposed model was also applied to natural data sets of the seismic velocity structures in the observations and so on. So, so basically there are two kinds of seismic waves: the P waves, which are fast, the pressure waves, these are the primary seismic waves, and then there are the S waves, which are the slow shear waves, they are the secondary waves. So we have observations of their velocities of both the P waves and the S waves at different places on the earth at certain depths and so on. Now there are some properties of the earth, like earth's mantle. These are called the porosity and the effective aspect ratio. So both of these factors, these properties, they impact the velocities of the seismic waves. Now the task here is that based on the sparse observations of the seismic wave velocities, we need to estimate the porosity and effective aspect ratio in different places, in different points of the like Earth's interior. Now the porosity property has spatial autocorrelation. That means at two locations which are close to each other, the spatial properties are likely to be very similar. So what we need to do is to define a graphical model with velocity nodes and porosity nodes, and then define the potential functions approximately. I mean, not only porosity nodes but also the the effective aspect ratio nodes. So like some of the nodes will be corresponding to the observed variables and some will be corresponding to the latent or unobserved variables. So if you remember the various graphical models which we had studied in one of the earlier lectures, so there are, like for Markov random fields, we have some nodes corresponding to variables that are observed, and we will also have some nodes corresponding to the variables that are not observed, and then there will be edges between different kinds of variables, and each of those edges will have the edge potential functions also. So the like first of all, the thing is we can express the Vp and Vs, that is the P velocity and the S velocity, as some functions of the two things we are interested in, phi and alpha. Phi is the porosity and alpha is the effective aspect ratio. Now let us say that these functions f and fp and fs, let us say that we already know those functions from our domain knowledge of seismology, but we do not know phi and alpha at all at all locations. So now what we do is, so like first of all we we define some kind of a probability distributions on Vp and Vs at any location. So let us say there are total n locations or grids where we will we will do our study, and let us also say that in each grid these the phi values, we have unique phi and alpha values. Also let us further assume that the Vp and Vs, these velocities, they are independent of each other, so that this joint distribution can be factorized as a product of their marginal distributions. Then what we finally have to do is, or what we intend to do is to create the posterior distribution on this porosity and aspect ratio depending on the observations that we have. So that is to be written in this way. Now like our aim is to estimate this kind of a posterior distribution. So for this purpose we define what is known as the energy of the Markov random field, where this energy like if you remember, in a Markov random field the joint distribution is a product of the different clique potential functions. Now instead, like in a normal graph, a clique may just mean that individual nodes which are cliques of size 1 and edges which are cliques of size 2. So for the for that we need to define the the node potentials are there. Then on top of that we put the edge potential functions, and the edge potential. So there are two kinds of edges. One is the edge between the 5 variables or the alpha variables at different locations, and then there are edges between the 5 variables and the VP variables and VS variables and so on. So in case of those, the later kind of edges, where like for at any location the corresponding VP is connected to the properties phi and alpha. So for such edges we have like the edge potential functions, and then for the edges that are connecting to 5 variables we have this kind of a edge potential function. So as you can see, phi I minus phi j. So let us say that like it's an arrow between the 5 variables at location I and location j. So between them we just simply have the edge potential is simply the squared difference. So like if two of them are close to each other, then like that should have a high probability. Those 5 values are close to each other, that should have a high probability compared to the situation where the 5 values are broadly different. So this is based on the special autocorrelation which we talked about. So a similar property also holds for alpha, and of course there is a variance component for both phi and alpha, so they are encoded like this. So accordingly we have this kind of what is called the energy function of the Markov random field, which is nothing but a representation of the joint probability distribution of all these random variables. So these z phi, z alpha, these are known as the partition functions that are necessary to make sure that it is indeed a joint like a valid probability distribution, that is the sum of these values of the energy values for the different combinations, they all add up to 1 in the proper way. So now what we need to do is, so first of all there are these the variables phi and alpha, the latent variables, and then there are the different hyperparameters, these sigmas and so on. I mean also these FP, Fs, these functions, they may have their own hyperparameters which have to be estimated. So what is first done is that like all the parameters, let us say we represent by theta. So for the time being let us ignore the latent variables and let us just try to estimate a posterior distribution on the hyperparameters based on the observations Vp and Vs. So we do this kind of marginalization where we integrate out the all possible values of phi and alpha, and then we get a posterior distribution of the parameters. Now this kind of integration, this cannot be done numerically because it's that might be intractable. So this kind of integration is again done through MCMC techniques, so that is based on sampling. So once we get this f theta, that is the posterior distribution of the parameters, then we choose the map estimate of all the parameters, that is the parameters which maximize the value of this posterior distribution. That in a sense gives us the optimal values of the parameters. Then using the optimal values of the parameters, again we calculate the map estimates of phi and alpha. So note that phi and alpha are not individual values, but they are like they are defined separately for each of the different locations that we are considering, so that we will get n values of phi and n values of alpha. And like we need to do it in many trials, and we can expect that like as we or many iterations, and as we do the further and further iterations, we can see the convergence. So unless the convergence happens, we cannot expect to find the like any optimal values. And like here as their studies shows, their experiments show that as they keep on doing more and more trials by this like using this optimization, they see the some kind of convergence of the root mean square error, That means, so like in the held out set, which or rather on which they are validating, they find that using this approach, the estimated value of phi and alpha are coming close to the known values. And so so this might be a possible plot of the phi, and which they, so the observational data are of course Vp and Vs. So like this primary wave, it has higher velocities up to 8 kilometers per second, while the secondary wave, it is usually slower, about 4 kilometers per second. So this is, let us say, over a spatial region. So as you can see, this is gridded data at different locations, the Vp and Vs vary. So using this and the corresponding target variables are phi and alpha. Let us say these are their spatial distributions. So this is like, this is the training data. This is what is I mean, this phi and alpha is what is already known by some kind of measurement. Now what we need to do is to based on these observations of Vp and Vs, we need to estimate the phi and alpha. So we can either go for some kind of deterministic method which was known to the seismology researchers earlier, that is where they basically tried to like invert this function Fp and Fs in some ways. And so like this is the kind of estimates of phi which and alpha which they get using those methods, and these are the estimates of phi and alpha which is obtained by the MRF methods. So as you can understand, in the like you can compare these plots or these maps with the true the targets or the true values, and you can see that the estimated values are like very similar to what is the actual values. But if you compare these maps which are obtained by the old deterministic methods, you can see that there is hardly any similarity. So that shows that using this MRF model, we are able to get a much better estimate of the maps of the unknown variables. So these are the references of the two papers that we discussed today. So the key points to be taken away is so there are basically that's the key point. These are the key points to be taken away, which we discussed, that Markov random fields are capable of incorporating the spatial autocorrelations, and this in turn helps us to identify the relation or estimate the various unknown variables. And secondly, like when we have observations or multiple observations, none of which are reliable of a particular quantity, we can express the particular quantity as a linear combination of all those observations along with some uncertainty estimates, and then not only the linear coefficients for that relation as well as those coefficients, they can all be estimated using some kind of a using the inference algorithms like Gibbs sampling and optimization. So that brings us to the end of this lecture. In the further lectures, we will see some more applications of machine learning to discover new insights in earth sciences. So till then, bye bye.